that exist as molecules. So pure hydrogen, pure nitrogen, pure oxygen, and the pure halogens exist as diatomic molecules under normal conditions. And most of everything we do are going to be under normal conditions. And so you're going to need to memorize these, memorize them big time. So hydrogen, nitrogen, oxygen, and all of the halogens. And the halogens are everything from fluorine to iodine. Acetine is a little bit of an outlier, even though it's in the same group. So that's to say, when we say the molecule of hydrogen, it's H2. A molecule of nitrogen, N2. Molecule of oxygen, O2. Molecule of fluorine, F2. A molecule of chlorine, Cl2. A molecule of bromine, Br2. Molecule of iodine, I2. So there are going to be a couple of different mnemonics to help you memorize this. And the reason you need to memorize this is because quite often on the AP exam, you're going to have to use these because these really are pretty darn common molecules. You're going to have to use the molar mass of one or all of these maybe in your calculations. And so when you're calculating the molar mass, if you're trying to use nitrogen's molar mass, a molecule of nitrogen, and you only write down 14.01 for your molar mass of N2, you're going to get the wrong answer. Because N2 is not the mass of one nitrogen. No, no, no. It is the mass of two nitrogens. 20.02. So there are a couple of mnemonics. You have Brinkelhoff, right? Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, right? These will help you remember. Also, anything that's a gen is another way to remember it, like we have written here. Hydrogen, oxygen, nitrogen, and all the halogens. Right, so whichever mnemonic helps you remember that, go for it. A couple of others that you might see, you do not have to memorize them, but I don't want you to freak out if you see them. Phosphorus 4, P4. It's a tetratomic form of elemental phosphorus. It's an allotrope. It's made up of the exact same stuff, phosphorus. It's just shaped in a different way. They're bonded together in three-dimensional space in a slightly different way, even though it's all phosphorus. S8, right? Sulfur's elemental form, also an allotrope. Carbon, diamond, and graphite are things that you've heard of. They're both pure carbon. However, they are arranged in three-dimensional space in different ways, different covalent networks of atoms. There's another allotrope of carbon that's actually very interesting. It's called the buckyball. Oh, buckyball. You don't need to know this at all. I mean, you might see it, might make you more comfortable with it, but you're never going to be asked a question about this. It's actually an allotrope of carbon that is a carbon-60. And buckyball, it's actually named after the person who described it. He has a big old long name that starts with buck. That's why it's buckyball. But he developed a way that with 60 carbon atoms under the appropriate conditions, right, it has to be maintained, but under the appropriate conditions, carbon atoms will actually form what looks very similar to a soccer ball with alternating hexagons and pentagons, which with each of the vertices on that soccer ball being a carbon atom. It's actually one of the bases for nanotechnology, and hopefully you remember nano refers to 10 to the minus 9. Doesn't just mean small. Nano is small, but because it means 10 to the minus 9. So remember your diatomics, and please do not be intimidated on the AP exam if you run into a question that asks for an allotrope. You won't have to memorize them. The question will tell you what the allotrope is.